English?
Yeah, I can speak English.
Or Nederlands?
No, I am from Denmark.
Okay, in English then. I give you the microphone, it's still on the...
Good morning, ladies and gentlemen. I'm really happy to introduce our first speaker today, Jens Kaad. Morita equivalence is spectral.
Thank you very much. And I also wanted to thank the organizers for inviting me. I'm really, really glad to be back here in Nijmegen. So, in noncommutative geometry, at least as far as I've understood it, we want to analyze algebras by applying a geometric perspective. And the framework for carrying out this analysis is given by a spectral triple, which you can then think of as a noncommutative version of a manifold. So if this point of view is accepted, I think it's very natural to ask the question: when can you say that the two algebras are the same as noncommutative geometric objects? That is, when do they admit the same spectral triples? Or when is there a bijective correspondence between the spectral triples over one algebra and the spectral triples over the other algebra? So the main idea that I will investigate in this talk is that if you have two algebras that are Morita equivalents, then they should be the same as noncommutative geometric objects, and the Morita equivalence bimodule should implement this bijective correspondence between the spectral triples over one of the algebras and the spectral triples over the other algebra. So I will start out lightly by just explaining your concept that you all know very well, which is that of a spectral triple. But it will be a minimal definition, so there will be no J operator or anything like that. So it's really more like an unbounded K-homology class. So here it is. So you know a spectral triple. It's a triple, and well, the first ingredient is a star algebra, which is represented in a. So I want to be represented in a non-degenerate fashion on a separable Hilbert space. But the star algebra need not have a unit. Okay, and then the third ingredient here is some self-adjoint unbounded operator, D, which acts on this Hilbert space. So it has a domain which is dense inside H, and D is really equal to its own adjoint. It's not just symmetric. So it's not just included in its own adjoint, D is equal to its own adjoint. And then there are conditions. So the first one is that, okay, since D is self-adjoint, I have the resolvent of D, and I can multiply that with an element in the algebra. And this has to be a compact operator on the Hilbert space. Okay, the second condition is that the domain of this D is an invariant subspace for any algebra element. And then this commutator with D and A, it makes sense on the domain of D as an unbounded operator. And this unbounded operator then has to extend to a bounded operator, which we call D of A. So that's like the minimal definition of a spectral triple. And I will forget about grading operators at the moment. So then we come to the next main concept. So when are two unital star algebras going to be Morita equivalent? And during this talk, you will see three different notions of what it means to be Morita equivalent. And the first one, which I will start with, is also the oldest. So I think it dates back to the 1950s. So, and that's a purely algebraic version of what it means for two algebras to be Morita equivalent. So, okay, so here's the definition. So two unital star algebras, they're going to be Morita equivalent when there exists some orthogonal projection inside the n by n matrices with entries in B, and then there are two conditions. So the first one is that the unital star algebra, it has to be star isomorphic to the bilinear in the morphisms of this finitely generated projective module which is associated to your projection. So that's the first condition. The second condition says that this finitely generated projective module should be full. And in this context, it just means that I can find elements inside this module so that when I take the inner products of psi j with psi j and I sum them up, I get the unit in my algebra. And then you can check that this is an equivalence relation. Product. Okay, so it's this module here, it sits inside the free module. Yeah. But you cannot write it like that. I mean, yeah, it's what it is. Yeah.
Why do you need the unitality here? I mean, you can design a slightly more general definition. You can pick your projection in multiplayer algebra or whatever, one-point unitization. Is there a particular one here? Or
it's just to make it a little bit easier to begin with, okay? So for now, they are unital. It doesn't matter, I think.
What is saying? To be unital or not? Pick it up in multiplier or something else. For finite things. Yeah. But n is not to be n.
No, it did not be the same number of elements. Yeah. It did not be the same, no. Okay. Yeah, and then I think that it's more or less like a folklore result. I mean, I have not been able to find a precise reference for this result, but I know that, I mean, at least Wenzeler has been thinking about what it means for two spectral triples to be Ritter equivalent, but I believe that the point of view is slightly different here because, as far as I know, his notion of being Ritter equivalent is not an equivalence relation. It's not symmetric. But this point of view is different. I mean, here it's really two algebras that are Ritter equivalent, and this has consequences for what happens for the spectral triples over these two algebras. Okay, so here's the theorem. So it says that if you have two Ritter equivalent unital star algebras in this sense, then indeed you have this bijective correspondence between the spectral triples over A and the spectral triples over B. But there's a subtlety here, which is contained in this parenthesis at the end. So it says that this is actually not really true as it stands. You need to divide out by two equivalence relations. And the first one is, okay, if I have a spectral triple and I have a unitary operator, I can conjugate it. And I obtain a new spectral triple, and I think about them as being the same, up to unitary equivalence. The other one is that if I have a spectral triple together with some bounded operator, bounded self-adjoint operator. So you might dislike me for this, but then you can then you can perturb your spectral triple by adding this bounded operator to the Dirac operator. And you get a new spectral triple. And I will think about these two spectral triples as being the same. And I will say they're bounded perturbations of each other. So in particular, there are no non-trivial finite dimensional spectral triples from this point of view. So you will dislike this, but yeah.
And you have the first order condition.
There's no J.
You have the first order condition. There's not here.
No.
If it's finite dimensional,
Oh, okay, no J.
so it's finite dimensional, then all operators are bounded.
Yeah.
So in particular, all of them are equivalent to the operator where you have 0 as your Dirac operator. Yeah?
Do you assume in your definition of a spectral triple that the kernel of the commutation with D is only proportional to the constants, or
No, nothing like that.
It could be that the kernel is bigger.
I don't care. I don't care.
0 is fine.
The D equals 0 is fine, except that if the Hilbert space is infinite dimensional, then the result will never be compact, right? Hmm. Okay, so it's true up to unitary equivalence and bounded perturbations. All right. Moreover, this bijective correspondence, it's really going to be explicit. And it's given by the most simple version of the unbounded Kasparov product, which in this purely algebraic context is, I had to name it quite a few people. So Kahn and Mathai and Rennie and Lord and Van Zuylichem and really, I think there are really many people who have noticed this construction. So the statement is, now you have this finite generated projective module over B, and it's given by this orthogonal projection P. Okay? And then you have any spectral triple over B. Then you can form a new spectral triple by taking the tensor product with this module. And it's now going to be a spectral triple over another algebra, and the algebra is going to be the endomorphisms, the bilinear endomorphisms of this module. Okay? That's a new algebra. And then I form a new Hilbert space. It's just given by, okay, I can look at n copies of the Hilbert space H, and I can cut it down by my orthogonal projection. Fine. And I can also cut down my Dirac operator by this orthogonal projection. And then I have to take the closure. I get a new self-adjoint unbounded operator. And the statement is that this is, again, a spectral triple and spectral triple for the algebra A. And this is the map that implements this bijective correspondence between the spectral triples over B and the spectral triples over A, when A and B are Morita equivalent. So, no, it's not automatically self-adjoint. You need to take the closure. Yeah. You need to take the closure. Okay, so now we come to the second notion of what it means for two algebras to be Morita equivalent. And this is due to Mark Riefel, dating back to the 1970s. But now you are working with a smaller class of algebras. You now only want to work with C-star algebras. But okay, I will admit that they are just sigma unital, so they need not be unital anymore. There could just be, sigma unital means there's a countable approximate identity. Okay, but the advantage you have when you work with C-star algebras is that you're allowed to use a more flexible class of modules when you want to find out whether two algebras are Morita equivalent. You are allowed to work with Hilbert C-star modules. And these need not be finitely generated projective. They can have countably many generators. And in fact, it's enough to have a countably generated dense submodule. So it's a much more flexible class of module than just the finitely generated projective ones. So here's the definition. Okay, so two sigma unital C-star algebras A and B, they're going to be Morita equivalent when you have this Hilbert C-star module X. So it's like a Hilbert space, but the inner product takes values in B, in a C-star algebra. Okay, so it's a Hilbert C-star module over B, and then there are conditions. The first one is that A here, it has to be star isomorphic. It has to be isomorphic as a C-star algebra to the compact operators on this C-star module X. And these compact operators, they are not compact in the sense of Banach spaces. They're compact in the sense of C-star modules. It means that being compact, there are norm limits of finite rank operators, where finite rank is defined in terms of the inner product and the module action. So they're really not compact in the sense of Banach spaces, even though X is a Banach space, but it's different concept. Okay, so the first one is that A star is isomorphic to this C star algebra of compact operators. The second one is, again, okay, X is full, but now it's a C star module. So there's this inner product which takes values in B, and I can look at the star subalgebra of B generated by elements of the form xi, eta, where xi and eta are in the module. And I'm just requiring that this star subalgebra is norm dense in B. Then we say that A and B are Morita equivalent. So, just as in the case of two Morita equivalent unital star algebras, when you have two Morita equivalent C star algebras, or two strongly equivalent C star algebras, strongly Morita equivalent C star algebras, there's a bijective correspondence associated to this Morita equivalence. But this time, it's not a bijective correspondence between spectral triples or the C star algebras. It's a bijective correspondence between the k-homology of A and the k-homology of B. So here comes the statement. So now we have two Morita equivalent sigma unital C star algebras, and then the k-homology of A is going to be isomorphic as a Z mod 2Z graded abelian group to the k-homology of B. And moreover, this map that you have from the k-homology of A to the k-homology of B, it's implemented by the bounded Kasparov product. So this Morita equivalence bimodule X determines a class in the KK theory from A to B. It's really just a class of this C star module, as we also saw yesterday. Yeah. And you can take the bounded Kasparov product by this class, and it gives you this bijective correspondence from the k-homology of B to the k-homology of A. So any class in k-homology is represented by a Fredholm module. And okay, I think it's fair to think of a Fredholm module as being a topological version of a spectral triple. And moreover, you can think of this bounded Kasparov product as being a topological version of the unbounded Kasparov product that we saw a few slides ago. So it's all very nice to extract topological information from C star algebras, but I still want to answer my first question, which was, okay, when can I say that two algebras are the same as noncommutative geometric objects? So when can I say something about the spectral triples over these two algebras? So I thought I could say something about the spectral triples when this bijective correspondence, this Morita equivalence, happened through a finite generated projective module. But I would like to work with a larger class of modules so that I can have countably many generators. And moreover, I don't want my class of modules to be so coarse as the Hilbert C star modules, because I'm not only interested in transporting topological information. So I have to find some kind of balance between these two different types of modules. And yeah. So the class of modules that I will be working with is maybe not familiar to that many of you, so I will just hang on. I will spend some time on really defining them carefully so you can see what it is. So it's a class of modules that are not purely algebraic, but they are not as coarse as Hilbert C star modules. There's some analytic information. Okay. So the first fundamental object that I have to start with is an operator space. Okay, what is an operator space? It's a vector space, fine. But then on top of that, you have norms. You have a norm on each n by n matrix with entries in X. So the n by n matrix is again a vector space. And then there are conditions on these norms. The first one is, okay, this vector space is a Banach space, so it's complete in that norm. Fine. The second one is that if I take two matrices and I form their direct sum, then the norm of this direct sum, so this block diagonal matrix, has to be the maximum of the norm of psi and the norm of eta. Okay, second condition. The third condition is that if I now have an n by n matrix psi with entries in X, and I have n by n matrices V and W, both with entries in the complex numbers, then I can look at the matrix product of V and psi and W because X is a vector space. I get a new matrix with entries in X, and I can estimate the norm. It just has to be dominated by the canonical C star norm of V as an n by n matrix over the complex numbers times the norm of psi times the canonical C star norm of W. So these three conditions tells you what an operator space is. And I think the main theorem about operator spaces is that, and it's due to Ruan, it says that any operator space, so any vector space with this collection of norms satisfying these three conditions, is completely isometrically isomorphic to a closed subspace of the bounded operators in some Hilbert space. So this is the power of operator spaces. There's this abstract characterization of what it means to be an operator space. At the same time, they are very concrete objects. They're just closed subspaces of bounded operators. So that's beautiful, actually. It means that you have a map from n by n matrices of X into n by n matrices over the bounded operators. These n by n matrices of bounded operators also have a canonical norm because they're just isomorphic to bounded operators on n copies of H. Okay? And this has to be an isometry for each n. That's what it means to be completely isometrically isomorphic. Yeah. So now we can define a nice class of algebras that we will work with. So, okay, we're going to work with what is called operator star algebras. So just hold on. I mean, so an operator star algebra is an operator space. Fine, it was just a closed subspace of bounded operators. But it has this nice abstract characterization. And then, okay, there's a product. and this product makes A into an algebra, and actually all of the n by n matrices are also algebras. And I'm just saying now that each of these n by n matrices have to be Banach algebras. Okay, I also want an involution. So I have an involution on A, and this induces an involution on n by n matrices over A. And in this way, each of the n by n matrices over A becomes a star algebra. And I'm now just saying each of these n by n matrices over A is a Banach star algebra. It's the only thing. So this is completely isometric involution. Final condition, okay, I want it to sit densely inside a C star algebra. So there is some C star algebra A, which again is sigma unitil, and then I have this star homomorphism from A to capital A, and it respects all the structure, and it's completely contractive. Okay, so examples. First example is any C star algebra. Any sigma unitil C star algebra is an operator star algebra, because I have a canonical matrix norm on n by n matrices over a C star algebra. There's a unique C star norm. When I equip these n by n matrices with this unique C star norm, I get an operator star algebra. But there are more examples, and these are truly geometric, at least from my point of view. So here's another very good class of examples. So now we start with just a star algebra. And okay, you have another, let's say, sigma unitil C star algebra B. But this you can think about as bounded operators in the Hilbert space. Okay. That's typically what B is. And then you have some injective star homomorphism, pi, okay, from A to B. That's like a representation of A on a Hilbert space. And then you have a derivation, some closed star derivation. And this usually comes from taking commutators with an unbounded self-adjoint operator, which lives on your Hilbert space. Associated to this data, you can construct an algebra homomorphism from A into the 2x2 matrices with entries in B. And it's just going to send A to this lower triangular matrix with pi of A on the diagonal, and then the derivation applied to A in the lower left corner. And this is really an algebra homomorphism. But you see that it's not a star algebra homomorphism, because when I apply the star on the left-hand side, on the right-hand side, it flips, and it becomes upper triangular instead. So this can never be a star homomorphism. But I still get that actually this involution on the right-hand side, it agrees with the involution on the left-hand side up to conjugation by a unitary operator. And this implies that you really get an operator star algebra out of this. So you also have control over the involution on A. And the operator star algebra comes from the canonical matrix norms you have from the 2x2 matrices over B and this algebra homomorphism. So in particular, any spectral triple has a canonical operator star algebra associated to it. But this derivation is just a commutator with a Dirac operator.
Yes, when you talk about derivation from A to B, I guess it involves pi.
Yes, yes, yes. B is a bimodule over A. Yeah. Well, it's a bimodule over A, so then I can talk about derivation. No, the derivation is already closed. Yeah, yeah.
It's also relative to pi.
Yeah, yeah. But this map here from A to the 2x2 matrices over B is going to be, I mean, yeah. A is already closed in that norm. Yeah. This you can check. Okay, so I have to say now that if you had this notion of an operator star algebra, if you start forgetting two of the conditions, if you forget that you had the involution, and you forget that there was a C star algebra sitting around it, then you arrive exactly at the concept of an operator algebra, which has been studied very intensively by a number of prominent people. So I should name William Arveson and David Bletcher and Gilles Pichet. Should name a few of them. But here we have a little bit of extra data. We also have the involution, and we know that it sits densely inside a C star algebra in a way that preserves all the structure. It's more like A is really like C1 functions on a manifold. C1 functions vanishing at infinity on a Riemannian manifold. That's an example of A. And the derivation would be the exterior derivative. Okay. Yeah, so these people, they also found a relevant class of modules over operator algebras. Maybe what is called operator bimodules. But we want to remember that there was this involution and that my algebra sits densely inside a C star algebra. So I need to work with a kind of operator bimodules where there's also a Hermitian form. And it should sit densely inside a C star correspondence. So here's the definition. Then you arrive at what it means to be a differentiable correspondence. So I'm sorry, there's a lot of things that I have to go through in order to get to my main result. But I hope you can hang on as long. Okay, so what is a differentiable correspondence? Again, it's an operator space, so it's a closed up space of bounded operators. And then you have, okay, it's a bimodule, so there's a left action of A, there's a left action of B. These actions extend to n by n matrices, and all of them have to be contractive. So the n by n matrices over A is a Banach bimodule over the n by n matrices over A and the n by n matrices over B. Okay? I'm just keeping track of everything that happens at the matrix level all the time. But otherwise, all the definitions are very similar to what you have for Banach algebras and Banach modules. And then you have this Hermitian form. So you have a Hermitian form with values in B, and this Hermitian form, it has to satisfy the Cauchy-Schwarz inequality. And it has to satisfy the Cauchy-Schwarz inequality for all matrices over X. So there's also a Hermitian form from n by n matrices with entries in X to n by n matrices with entries in B, and all of these have to satisfy the Cauchy-Schwarz inequality. Okay, very good. Finally, everything sits inside a C-star correspondence. So there's this injective homomorphism, so it preserves the Hermitian forms and the bimodule structure from X into capital X. And capital X is a C-star correspondence from the C-star completions of A, and from the C-star completion of A to the C-star completion of B. So capital X is just a C-star module which comes equipped with a representation of the C-star algebra A. And there are some technical conditions. X has to be countably generated and non-degenerate. So again, examples. First example is any C-star correspondence. Whenever you have a C-star correspondence from capital A to capital B between two sigma-unital C-star algebras, this is in particular a differentiable correspondence. This inner product. You mean, or the norm on matrices? But, okay. It's not exactly what you do, so you have, okay, I will just write here. So, Mn of X, again, when X is a C-star module, there's an inner product with values in n by n matrices over B. And this you use to define the norm, just in the usual way.
But that's not part of the definition here, that it defines the norm.
Yeah. So it's quite important here that this Hermitian form that you have on X, in general, it doesn't control the norm. So the norm on X is something separate from the norm coming from the inner product. These are two very different things. I'm only saying that it satisfies the Cauchy-Schwarz inequality. When X is a C-star correspondence, then the norm does come from the inner product. But this doesn't happen on X in general. So again, okay, there are many more truly geometric examples of this. For example, coming from Hermitian connections. Usually X is a domain of some closed Hermitian connection. So that's what it is.
Why do you call it differentiable? Where is the D?
I mean, it's a word. Because I'm thinking of X as being the domain of a connection.
Which is going to be introduced. Or
Yeah, it's very similar to the previous example you had.
It's an operator star algebra correspondence that you are defining.
Yeah.
Call it.
Oh, well, I can call it what I want, but okay, yeah. It's a fair comment.
Analogous to respectful
so it's a way of transporting information from one spectral triple to another spectral triple. So it's a way of constructing new spectral triples out of such a differentiable correspondence and an old one.
This you're going to explain.
This I will actually not explain, but you can read. Because I have explained this many times already. I will not do it again. But yeah. I'm sorry about that. Should be more careful. Okay. Now. Yeah, but you can use this differentiable correspondence to move spectral triples from B to spectral triples on A. That's the point. Yeah. Okay. Okay, so in order to define what it means to be Morita equivalent now, we also need to have a tensor product of this kind of structures. And I'm going to use here the tensor product of operator spaces par excellence. And it's the Horup tensor product of two operator spaces. And there's a very nice theorem due to David Bletcher that says that if you have two C-star correspondences and you take their balanced Horup tensor product, what you get is completely isometrically isomorphic to the interior tensor product of C-star modules. So this balanced Horup tensor product is a nice generalization of the interior tensor product of C-star modules, but it applies to a much larger category of modules.
What does balance mean?
Balance means that it's a tensor product of modules. So x times b tensor y is x tensor b times y. So it's it's just terminology. Yeah, that's what it means. It's a tensor product of bimodules. Yeah. Okay, so this proposition says there is this tensor product, and it's going to be a new differentiable correspondence. So x is differentiable correspondence from A to B, and y is from B to C. I can form this tensor product, and I obtain a new differentiable correspondence from A to C, and it has some C-star completion. And the C-star completion is going to be the interior tensor product of the C-star completion of x and the C-star completion of y. So everything matches up very nicely here.
How does the emission in upper products work?
So it's a usual formula. So it's psi1, it's a 1. Yes, that's a new Hermitian form. Yeah, it goes like that. But the norm is more complicated. The norm doesn't come from this. Yeah. Let me see. Yeah, so there's already a notion of what it means for two operator algebras to be Morita equivalent. And this has been developed by David Bletcher and Paul Muley and Vern Paulsen, just to name some of the people that have been involved in this. But I found that their notion of what it means for two operator algebras to be Morita equivalent is too rigid to shed light on the geometric questions that I had in mind to begin with. So actually, in order to get a nice notion of Morita equivalence, I have to introduce an extra equivalence relation, which is not just mere unitary equivalence of two differentiable correspondences. It's more flexible than that. And you will see now what it is. So we say that these two differentiable correspondences, they're going to be in duality. So x has a C-star completion, which is this capital X, and y has a C-star completion, which is called capital Y. These two, capital X and capital Y, are going to be unitarily equivalent. So I have this unitary operator between the C star completions. Okay? And then there are conditions. Okay, first one is clear, just that U intertwines the left actions. That's okay. No surprise there. The second one is more interesting. So now I can take an element inside my differentiable correspondence, X, and I can apply my unitary operator to it because X sits densely inside capital X. Then I can look at the inner product with eta, where eta sits inside the differentiable correspondence Y. A priori, this only lies in capital B because it's the inner product on the C star correspondence, capital Y. But I want it to lie in the operator star algebra B. So a little bit finer. Okay, so then I have a pairing between X and Y with values in this operator star algebra. So it just sends psi and eta into U of psi inner product with eta. And this pairing has to be completely bounded. So it extends to a pairing on n by n matrices. All of them, there has to be a uniform bound in the Cauchy-Schwarz inequality. So there's a constant in the Cauchy-Schwarz inequality here, but there's a uniform bound on this constant. So it's not just completely contractive. Okay, so now we are finally ready. So what does it mean for two operator star algebras to be Morita equivalent? Okay, it means that you have a differentiable correspondence X from A to B and Y from B to A. And okay, they have to be compact. And this just means that when I look at the C star completion, then the left action of the C star completion of A factorizes through the compacts. So that's what it means to be compact here. And then, okay, I can form these tensor products of differentiable correspondences. The tensor product of X and Y over B has to be in duality with A. And the tensor product of Y and X has to be in duality with B. And examples. So first example, if you have now a Riemannian manifold, and you take another Riemannian manifold, M prime. So M and M prime are the same as manifolds, but the Riemannian matrices are only the same up to a conformal factor. So Riemannian matrices are only conformally equivalent. Okay, then I have two different operator star algebras. I can look at the C1 functions on the manifold that vanish at infinity on M, and the C1 functions vanishing at infinity on M prime. So these are really quite different, because what it means to be a C1 function vanishing at infinity, it's also that the exterior derivative has to vanish at infinity. And this is symmetric. Because what does it mean that the exterior derivative of a function vanishes at infinity? To define that, you need to use symmetric. Yeah. You have the summation formula, the cotangent boundary, you have to use that. So these are a priori quite different operator star algebras. But you can prove now that they are going to be Morita equivalent. So I'm not saying anything about M being complete, or it's just any Riemannian manifold. Okay, second example. Now I have a Riemannian manifold, and there's a discrete group acting on it by diffeomorphisms. And this discrete group is going to act freely and properly. And then there are some conditions on the relation between the action and the Riemannian metric. So the first one says that the exterior derivative of each of these diffeomorphisms has to be a bounded operator. Okay, and the second one says that there's a uniform bound on these operator norms. So in particular, if you have an action of G by isometries, this is fine. Yeah.
Why do you need the group to be discrete, since in Morita equivalent a la refold this is always true?
No, it's for discrete groups.
No, I think in refolds for locally compact groups under your definitions.
No, I took this from Kahn's book, and he's stressing that it's a discrete group. Yeah. Okay.
The question is why?
But this enters in a very crucial way. in the proof. Yeah. Well, I would have done it for a non-discrete proof if I could, but yeah. Okay, so then you have these two operator star algebra. You can now form an operator star algebra version of the reduced cross product of G, but G now acts on the C1 functions, vanishing at infinity on this manifold. And this operator star algebra is going to be Morito equivalent to the C1 functions vanishing at infinity on the quotient manifold. So that's example number 2. Example number 3, if you have an operator star algebra, you have a closed right ideal inside this operator star algebra. Okay, then you have the C star completion of this right ideal sitting inside the C star completion of A. And so this is actually this is a C star module. You can think of it as a C star module over A. And this C star module has to be countably generated. So very weak condition. Secondly, this C star module has to be full. So again, I can look at the star subalgebra of A generated by these inner products. So in this case, this just looks like psi star times eta, where psi and eta lies in L. So, and then it follows that actually this hereditary operator star algebra coming from the right ideal, which is the intersection of L with all elements of the form psi star, where psi is in L. This is a new operator star algebra. It's going to be Morito equivalent to the full operator star algebra A. So I think that, as you say, class, I mean, that you can construct more examples of geometrically Morito equivalent operator star algebras with some work. I've just taken these examples because they are from the book on noncommutative geometry by Alan Kahn from '94. So it's from the Bible on noncommutative geometry. But in the book, there are examples of strong Morito equivalences. But here you see that with a little extra geometric information, you can promote these examples to be statements about some relevant dense star subalgebras. Now I would love to say that if you have two Morito equivalent operator star algebras, then there's a bijective correspondence between the spectral triples over A and the spectral triples over B. But this I don't think is true. Because in order to have such a statement, you need to work with a more flexible notion of what it means to be a spectral triple. That is, you have to twist the commutator condition by an extramodular operator. So you have to work with twisted spectral triples in order for such a statement to be true. But if you're willing to do that, there's a bonus, okay? So it's here. So now, if you have two Morito equivalent operator star algebras, in this sense I have explained to you, then indeed there's a bijective correspondence between the twisted spectral triples over A and the twisted spectral triples over B. Where this twist is given by some extra automorphism, okay? And again, okay, it's only true up to twisted bounded perturbation, so there's a notion of twisted bounded perturbation of two spectral triples. And unitary equivalence. We have to mod out by these two equivalence relations again. Moreover, this bijective correspondence, it's implemented by the unbounded Kasparov product. So you have these differentiable correspondences, x and y, that implement your Morito equivalence between A and B. You can take an unbounded Kasparov product with x and an unbounded Kasparov product with y. And this gives you the bijective correspondence between these spectral triples over A and spectral triples over B. So this unbounded Kasparov product, many people have been working on it and are still working on it. So I'm just naming a few here. So Mesland, who is here, and then Lesch, And I think I also have to mention this mysterious person K.
You need to sit in the category of twisted spectral, twisted cluster
Mm-hmm.
because of the connection you need to use for your bounded transverse product.
Yeah, so for me, there are plenty of reasons for that. I mean, it's yeah. So should I really give an example? Yeah, yeah. That's what you have to do. It's because in general, when you work with such a general definition of a differentiable correspondence, you do not have nice connections. Yeah. Okay, I can show you one example because Richard says so. How do you do this? So it's one I usually do. So you have U is an open subset of the real line. Then you are in this situation, so you can look at the C1 functions on U vanishing at the boundary. And this is a differentiable correspondence from
Can you get some more light?
yeah. You can also just shut off that one. So then you suppose that there's a function. Some positive function. Let's say it's just defined on the real line such that the points where this is non-zero, that's exactly the set U. So U is just the place where some smooth function convex support does not vanish. Okay? So now I have a canonical spectral triple here on the C1 functions on the real line. And I have a differentiable correspondence. So I can move that to a spectral triple over this non-complete manifold. And
You know what is a D?
yeah, so D here, so here you have IDDT. And when you take the product now, this unbounded Kasparov product, this one here becomes, so you can move it to this one, it becomes F IDDT F. So that's the product. Yeah. When you do this in a noncommutative fashion, then you get an extra modular operator coming from the fact that your X here would not necessarily commute with the algebra action from the left. So that's why you see the twist. It's really, yeah. So it's a very natural construction, but you just need to pass the twist with things. Yeah, in this example it is, but you can. But in general, I could also just have some spectral triple, okay? So A, H, D, and I fix some element in A. Then I can look at X, A, X star. So that's the analog of C1 functions vanishing at infinity on the boundary of U. So this sits inside A, okay? Again, I have a differentiable correspondence between these two things. It's just given by the right ideal. So then I have XA is differentiable correspondence from xa x star to A. So then I can move the spectral triple to this algebra here. The way I do it is that I just multiply D with x and from the left and x star from the right. So you get a new one, which is xa x star xh xd x star closure. That's a new spectral triple. But it's when A is noncommutative, this is going to be twisted. I mean, it's a very natural construction, but things become twisted. Yeah. That's, yeah. You can see, yeah. I mean, it goes like this. It's extremely explicit. I mean, you choose the sequence of generators of your module and use that to form the Kasparov product. It's really very explicit. Yeah. But so in general, you don't have nice generating sequences for your module. Even though it might be generated by a single element, this need not be nice. Yeah.
So imagine you can iterate this and speak about smooth.
Yeah, so that's maybe possible, yeah. It's, not necessarily.
For instance, here, I mean, if you take C01 function,
Mm-hmm.
because you take DT.
It doesn't have anything to, I mean, of course it has something to do with it, but this is just defined in terms of the exterior derivative and the Riemannian metric, so it's an intrinsic thing.
Yes, it allows the triple with DT to be spectral.
Yes. Yeah. So you have this commutator has to be a completely bounded map.
So,
Yeah. Yeah, otherwise you cannot do anything like that.
The unitary operator here will be from the two algebras up to unitary equivalence. So in this case here, you would twist the tensor there is always the unitary equivalence.
Yeah.
In this example, what would be the unitary operator?
But here's okay. I'm not talking about Morita equivalence at this point.
You would call them equivalent?
Well, they will be, yeah. They will be, yeah.
Change the measure on the.
Yeah, I think they will be the same. I mean, up to Morita equivalence in this sense because of the first example. If you have two conformally equivalent things, then yeah. Yeah, so that's a good point. But for me, I'm interested in doing analysis, and therefore I just want to work with unbounded operators and not bounded ones. But okay, I mean, one can discuss and see whether you can find a more subtle equivalence relation on spectral triples, which would not make all finite dimensional spectral triples look trivial.